In order to do a first derivative analysis, all we need is the first derivative. Now what we're going to do here is we're going to find where f is increasing, where f is decreasing. We'll find our local extrema, and we'll do all of this just from the first derivative line analysis. Now, the first thing we have to do is we need to find the critical points of f. Now, the critical points of f are where f prime are equal to 0 or undefined. So let's first find f prime. Here we have f prime is 3x squared minus 12. This always exists, so let's set it equal to 0. We can factor out a 3. We get x squared minus 4. And of course we can factor that using a difference of squares. That's x minus 2 times x plus 2. And this is all equal to 0. Therefore, we have critical points at x equals negative 2 and at x equals 2. We'll now do our line analysis in order to determine whether these are in fact extrema and not just critical points. So here's our line representing f prime. Here we have f prime is equal to 0 at negative 2 and f prime is equal to 0 at positive 2. Let's look to the left of negative 2 and let's plug it back into f prime. So let's check negative 3, for example. Positive, negative, negative, that's positive out here. Let's check between negative 2 and 2. How about 0? Positive, negative, positive, it's negative inside. Let's look to the right of 2. How about 3? Positive, positive, and positive. Now, we have a local max at x equals negative 2 because f prime is changing from positive to negative at x equals negative 2. Likewise, we have a relative min at x equals positive 2 because f prime is changing from negative to positive at x equals 2. Not only that, but this graph right here actually also tells us where f is increasing and decreasing. Remember that f increases when f prime is positive, and that f decreases when f prime is negative. So, let's actually write out our analysis. F is increasing on the interval from negative infinity to negative 2, not including negative 2 because f prime is 0 at our critical points, union from 2 to infinity because the f prime is positive in those regions. Moreover, f is decreasing on the interval from negative 2 to positive 2. F has a local max at x equals negative 2. And f has a local min at x equals positive 2. We can even find the maximum and minimum value of this function by plugging in negative 2 and positive 2. When we do that, we get f of negative 2 is equal to, let's see here. If you plug in negative 2, we have negative 8 plus 24 is 16 plus 5 is 21. And if we plug in positive 2, we get 2 cubed is 8 minus 24 is negative 16 plus 5 is negative 11. We can even graph this function and see how all this would look on the actual graph. Here's what this function looks like. Now f is increasing from negative infinity to negative 2, as we noted right here. And f is decreasing from negative 2 to positive 2, as we noted right here. And finally, f is increasing from positive 2 to infinity. Now it also looks like we have a local max at x equals negative 2, and we found it to be positive 21. And we have a local min at x equals positive 2, and it looks like it's, in fact, negative 11. So all of this we got from one line graph right here based on the first derivative. So our first derivative analysis is extremely powerful in that it can dictate to us the global behavior of our functions as well as the local behavior of our functions.